Continuing with our discussion on optics, let's now take a look at the concepts of interference and diffraction. As a wave, light exhibits diffraction and interference. When a wave encounters a barrier, so you have a light wave for instance, and it encounters a barrier, the part of the wave that passes through the opening in the barrier will spread out into the region beyond the opening. This is particularly true for waves that travel in all directions, such as light. This phenomenon is referred to as diffraction. Sound wave is also another wave that travels in all directions, so sound wave also exhibits the phenomenon of diffraction. So, for this topic, light, you have a light wave, encounters a barrier, and through the opening in the barrier, the light will spread out into the area or space behind the barrier. In essence, we can consider the light to being able to bend around the corners of the opening. Essentially, this is diffraction. Essentially, this explains why if you look under the table, the shadow under the table is not completely dark. Light is still able to reach areas under the table such that you're able to see things under the table. The shadow is not completely dark. Interference occurs due to wave superposition. Superposition of waves happens when two or more waves overlap at a particular point. For instance, you have a source, source 1, and then source 2, say light source. You have light source 1 emitting light in all directions. Source 2, source of light 2, also emitting light in all directions. If you look at any point in the surrounding space, you basically have two waves that will be overlapping at those points. So for instance, if you look at this point, distance R1 from source 1, distance R2 from source 2, at this point you have two waves overlapping. Light wave from source 1 and light wave from source 2, and superposition principle tells us that the two waves will interfere at that point. So consider two light sources with the same wavelength. So source 1, lambda 1, source 2, lambda 2. Lambda 1 is equal to lambda 2, so let's just use lambda for the wavelength. Superposition of waves tells us that due to the overlap of the waves, there will be interference of the waves. There are basically two types of interference. You have constructive interference and you have destructive interference. Constructive interference, you have the addition of the amplitudes of the waves. And destructive interference, you have the subtraction of the amplitude of the waves. So in terms of the intensity of the wave, for instance, the intensity increases if there's constructive interference, and the intensity decreases if there is destructive interference. In terms of light, you can think of it as in terms of the brightness of the light. If there is constructive interference, the resulting brightness increases, whereas if there is destructive interference, the resulting brightness will decrease. Constructive interference happens when the phase difference delta phi is equal to 2 pi n, while the path difference, delta r, is equal to n lambda. Delta r is r1 minus r2. So going back to the initial slide, you have r1 and you have r2. r1 minus r2, if the difference is equal to n lambda, you have constructive interference. N is equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on. For total destructive interference, for destructive interference to happen, the phase difference must be equal to pi n, while the path difference delta r must be equal to n plus 1 half lambda. Again, n here is equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on. For a more complete picture of interference and diffraction of light, you might want to look into the concept of Huygens principle. So consider that as reading assignment. This is particularly important in understanding, say, the diffraction of light, the bending of light around corners, and so on. Suppose you have a light and that beam of light is incident upon a double slit. You have a barrier with two openings, so slit 1 and slit 2. Essentially, you have two light sources, light source 1 and light source 2. These two light sources will be emitting light in the space beyond the two slits. If we place a screen a distance x from the two slits, the double slit, you will have two light waves that are overlapping at points on the screen. So you have superposition of the two light waves on the screen. You would have interference of the waves on the screen, points on the screen rather. The resulting interference will form an interference pattern of alternating bright fringes and dark fringes. Bright fringes, also called maxima, they are due to constructive interference, whereas the dark fringes, also referred to as the minima of the interference pattern, the minima are due to the destructive interference of our two waves. For d very much smaller than x, d is the distance between the two slits. Slit 1, slit 2, slit 1, slit 2, the distance between them is d. And x is the distance from the double slit to the screen. If d is very much smaller than x, that would result in the angles being very small. The angle is from basically the angular location of the point on the screen with respect to the double slit. So you have slit 1, theta 1, slit 2, theta 2. Theta 1 and theta 2 will be very small when d is very much smaller than x. So very small, they might as well be equal to angle theta, which is the angle from the middle of the double slit rather, to the point on the screen. So from the center line, with respect to the center line rather, you have angle theta. The maxima or the bright fringes are given by the following equation. D sine theta is equal to n lambda. And then you have y sub n is equal to nx lambda over d. Y sub n, you have different y, location on the screen, y. You have different values of y for the different values of n. N again is equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on. So again, these equations are for the maxima locations on the screen, for the locations of the bright fringes on the screen. On the other hand, if you are looking at the minima or the dark fringes on the screen, the location of the minima is given by y sub n is equal to n plus 1 half times x lambda over d. Again, n is equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on. If you look at the screen, this is basically the pattern that you will see. You have pattern of bright fringe, dark fringe, bright fringe, dark fringe, and so on. Take note of the following naming convention. For n is equal to 0, you have y0. You have the central maximum. So y0 for the bright fringe, you have the central maximum. The central maximum is the brightest spot on the screen. Then you have the first maximum, y1, second maximum, y2, third maximum, y3, and so on. And then on the other side, you have the first maximum, y negative 1, a second maximum, y negative 2, third maximum, y negative 3, and so on. For the minima, you also have y0, y1, y2, and so on. y0 is first minimum on this side, y1 is second minimum, y2 is third minimum, and so on. On the other side, it is y negative 1 that is the first minimum, y negative 2 that is the second minimum, y negative 3 that is the third minimum, and so on. So if the problem mentions first minimum, that's either y0 or y negative 1 for the locations of the dark fringes. While if the problem tells you the first maximum, that's y1 and y negative 1 for the bright fringes. So please take note of the naming convention for the interference pattern that you will see on the screen. So that's it for now. In the next video, we'll continue our discussion on interference and diffraction by looking at the concept of the single slit diffraction as well as the diffraction grating. So thank you for watching.